Okay, thank you very much. And thank you very much to KITP for organizing this amazing event. So I'll be talking about causality in the effective theory of gravity, but really the idea of what I'll be talking about, and particularly the first half of the talk, is what we hope to learn about gravity, in particular in the context of gravitational waves. Of course, gravity has been in impeccable agreement with all sorts of observations and experiments, from the smallest millimeter scales all the way up to cosmological scales, if you want to. But we do know that GR is really the leading term in an effective field theory. And so we like to understand whether there's any chance we could probe beyond that or not. And so I guess at the end of the talk, you'll decide for yourself one way or another. So I'll be talking mainly about what I'll consider high energy corrections to GR. Coming from irrelevant operators. But before I get there, let me just think of GR as an effective field theory with potentially infrared corrections to gravity. I spend most of my life in here, so I'll just give a few slides on that, which won't be exhaustive at all. So if you want to think of models of gravity in infrared as GR plus light degrees of freedom, or more generically as modifications of gravity in the infrared, this is not at all an exhaustive list of directions that people have been looking at in the past 20 years or so, but it's a little bit indicative to the type of symmetries you need to break in order to have any modifications of general relativity. And that really depends on how comfortable you are in doing any of that at all. I should mention there's also non-local modifications of gravity that I haven't even included there. So from modification of Lorentz invariance to modifications of the equivalence principle. And it's really up to you on whether you think those frameworks are fundamental and should not by any means be broken, or whether you like to contemplate what would happen if they do. But in terms of what happens for observable, if you attempt to break any of these type of symmetries, if you violate actually Lorentz invariance, that you don't typically need to introduce new degrees of freedom. You may or you may not do, that depends on the models. However, the main problems with modifications through breaking of Lorentz invariance is that they typically will propagate back into the standard model. However, from the point of view of gravity, if you do have additional degrees of freedom, they are typically weakly coupled to matter. I don't know if you can see this. It's really just symbolic. If you think of these additional degrees of freedom as they will need to be boson-like typically, so let me just think of them as being a scalar field. You have kinetic terms, you have potential terms with an effective mass term, and you really modify the effective coupling of this mode to matter, and you need that to be fine-tuned to be extremely small in order to be consistent with simple field force experiments, or if you want binary pulsars or this type of gravitational setup. Then people have been considering other modifications of gravity that carry light field and that do propagate field forces, particularly for cosmology. And in order to avoid any type of field force experiments coming from solar system test all the way up to gravitational waves emission from binary pulsars or binary system of other sorts, you need a screening mechanism, one of which goes under the name of the chameleon mechanism. And what it does is endowed the additional degree of freedom with an effective large mass in the vicinity of large density regions in the universe. So it plays a role in the mass. And this is not at all my work, but this is taken by a recent paper in here. And I think we'll hear more about some of those models. So from lunar laser ranging experiment, we can have some bounds on the parameters in this type of models, and gravitational waves possibly will go much further in probing this type of models. This, I should say, is from space, like gravitational wave observatory. And then finally, we've seen how we can lead to a modification of gravity, either consistent with observation by tuning the coupling to matter directly, by having a large mass in large dense region of the universe, or you can have modifications through the effective kinetic term of the model of the scalar field. And this goes under the name of the Weinstein mechanism and is really ubiquitous to a lot of models of modified gravity. And I think we'll hear a little bit more about this tomorrow, possibly, It's what happens, for instance, in Hundesky type of model, in massive gravity, multigravity, in many types of models. There has been some preliminary work trying to compute, use the amplitude methods that most of you are using in trying to make contact with between these models that exhibit a Einstein mechanism and any type of observables. I should say at the moment, this method applied to this type of models is in a very preliminary stage, because we really have to be working in a very weakly coupled region where the Einstein mechanism is not yet kicked in. And so one of the idea of this type of workshop for me, at least, is to try to understand whether there's any way we could extend these amplitude methods in a region where the Einstein mechanism is much more active. So I don't know how to do that. Maybe some of you have some ideas on that. What one can do is use instead other type of one-body effective field theories, where we get good insight on the corrections we expect from these type of models, or we can go numerically. And this is just an example of the type of numerical simulations you may have in a model of modified gravity that includes additional degrees of freedom that are screened via a Einstein-like type of mechanism. So this is completely numerical, but we can complement that with analytical results. So at the beginning of the movie, what you see is completely artificial, related to setting up the source. So we're setting up a system, and then we're imagining a binary system. It could be a black hole, it can be binary stars. So at the beginning, as you set up the system, you see that you have a lot of monopole and dipole radiations. This is just a failure of the numerical system. You're not conserving any sources when you switch it on. But as the system is relaxing to what would be the inspiraling phase, you see that the power emitted is dominated by the quadrupole. So roughly at this, not quite yet, but very soon, is dominated by the quadrupole. So you have quadrupole radiation from the standard tensor gravitational waves, and then you have additional quadrupole generation from these additional degrees of freedom, which are very much suppressed as compared to what you would have from gravity itself. And there are corrections that come in at 6th order in post-Newtonian. Okay, so I already spent more time than I wanted to into these modifications of gravity at the infrared. This is really a word of caution in what type of modifications you want to consider, what type of symmetry you may or may not be willing to consider, and the implications for theoretical implications and observational implications that this may happen. I have to say, if you modify gravity in the infrared, a lot of the observational consequences are very model dependent, and so this is a feature that one should try to address in the future and try to make it much more systematic. What I'll talk about for the rest of today is more, hopefully a more generic way to understand modification of GR coming from operators that are typically coming from integrating out heavy fields. And what you mean by heavy fields is really depending on how low energy scales you're willing to be working at. So we're probably thinking right here about the typical energy scales that come into our BK type of observations, but we can go much lower if you wanted to future space-based observations. So just the principle is that you may be interested in working at low energy, relatively low energy for gravity. And so below some energy scale, you can integrate out all the massive particles that come in above that scales. And you'll be led with an effective field theory of gravity below the mass you're interested in. What you have to integrate are possibly loops of lower spin particles, which are M-Planck suppressed, and then possibly there may be higher spin particles, which will come in as well. So the mass here, M, is related to higher spins if you had them. If you had some lower spin, it's really at loop level, and so this M is not the mass of this field, it's suppressed by the Planck scale as well. Now, I'll be interested in applying this in the context of black hole or vacuum solutions in 4 dimensions. So up here you have your effective field theory of this form. This is all very symbolic. The first term is the only one I haven't written symbolically. I should say I also have a cosmological constant problem, which is too big for me to solve. So I'm just gonna, I'm not gonna even write it down. So this is my effective field theory. And then you have different type of operators which you think just parameterize your lack of knowledge below some energy scales. Now, I'm going to want to apply this to a black hole vacuum solution in 4 dimensions. So I'm considering the vacuum. I'm not including a matter field. And in 4 dimensions, the dimension 4 operators are irrelevant. So I can really start with dimension 6 operators as typically my leading operators, my leading correcting operators that come into my EFT, and then dimension 8, etc. And we'll consider that any corrections to that corresponds to a low energy modification of gravity. So in the past 5 years or so, there's already been considerable work in those directions and trying to understand how these different type of operators affect various phenomena related for black hole physics or gravitational waves, all the way from in-spiral gravitational waves, and this is one of the first work on that, to quasi-normal modes coming from dimension 6 or dimension 8 operators, and constraints on the waveform in the early in-spiraling part of the waveform, and then bending, etc. And I apologize if I haven't written down your work in here. So this is indicative to the type of work that has been done. So let me start with just considering not everything that has been done, but the typical effect that you may be encountering in this type of effective field theory. And then very quickly, I'll see some of the problems that come in and how we need to abuse a little bit some of the effective field theories of going to regions where you may not feel comfortable with, and that's absolutely okay. So this is typically the hierarchy of scale I would feel comfortable with from the frequency of the wave, and M here you can consider being the cutoff of your low energy effective field theory. So if you're working above or close to the scale M, really you should reintegrate out your macroscopic physics, the additional degrees of freedom that have been just written down effectively from a low energy effective field point of view. I work with RS being the Schwarzschild radius last week, this is the quantity I'll be working with. You can typically work with that. And so being within the regime of validity of my effective field theory means that all of those scales in energy scale should be lower than that. So I'm going to ask myself to be in this region to start with. And then you can compute, for instance, the corrections to the quasi-normal modes around black holes. So for this region here, so the corrections to the quasi-normal mode will be very much suppressed. So for the dimension 8 operators, they go like this scale, which is very small. And for the dimension 6 operators, they're suppressed by 4 powers of that. So it's a little bit better than 8 power, but still it's quite unlikely that we'll be observing this very easily in the near future. Then you can think of the effect that come in the inspiraling phase. And this has been pointed out in some of these very nice papers for dimension 8 operators. It goes like, this is an 8 post-Newtonian parameter with 6 order of this coefficient suppression. So this is extremely small. And even for dimension 6 operators, this has been pointed out in this very nice paper here, it's a 5 post-Newtonian correction. So these are very much suppressed. And again, it's unlikely that we'll see any of those effects in the near future. I should say this have been computing using the stationary point approximation that was pointed out in this very nice paper quite a few years ago. So what has been suggested instead in this nice paper by Alessandro and collaborators is to consider the cases where you could potentially have some effect on the waveform, on the early part of the waveform. So you violate the condition written in here, and you allow for yourself a slightly different type of hierarchy of scales, where the cutoff is below the Schwarzschild radius, and so as to enhance the effect of this effect on the early inspiral. So in this case, you can trust your EFT in the early part of the inspiraling, and at some point you can no longer trust the EFT. That has the advantage of pushing up potentially the effect, but then you also, well, really you should just throw away, and that's what they do, just throw away the part of the inspiral where you're no longer in your low energy effective field theory. with the other half of the data, if you wanted to, you could also try to understand how the rest of the merger goes back into what you had predicted should be happen from general relativity. So you have modification of general relativity from those operators below some given scales, and then something happened. It has to happen extremely fast. I don't know how. And then typically you expect to have something else what you're no longer in control of your EFT at this point. So this is something people have been trying, and there's been some very nice work done for dimension 8 operators, where even though you're suppressed by this velocity, you may not be as suppressed by this power of the power counting of the operators. So this is typically what people have in mind from this type of considerations. If you did apply that to dimension 6 operators, just to get an idea of the scales involved for this to happen, you are compromised on both sides, right? You can either try to make the operators as important as possible by reducing the cutoff scale, but when you do that, you have less and less data available from early in spiraling because you go out of regime of validity early on. So you're really pushed between the two sides, and there's a very small window of opportunity, which depends on your sensitivity really, to being able to even observe such type of effects, even though you are a little bit compromised in the way you're considering your EFT. So in the very best case scenario, if you're very optimistic, you may be able to detect correction from your EFT that are coming at a scale to roughly 10 to the minus, let's say 10, probably 10 to the minus 13 electron volt, depending on the mass of your black hole. So this is a consideration you really need to keep in mind. So this is all I'm going to be talking about from the point of view of observability. This is the realm of what happens if you want to consider the effect of this type of operators, so the EFT of gravity with gravitational waves. Now, for the second half of what I want to talk about today is just going to apply theoretical considerations, so theoretical constraints on this type of effective field theory. And there'll be 3 different types of things we can think about. The first one is just at the level of the scale, whether this should scare us. It should definitely scare us, but whether this is already problematic or not. And then I'll talk about some very nice work that people have done putting some constraints from S-matrix S-matrix positivity bounds arguments. And then I'll go directly into causality constraints about black holes for this type of effective field theories, and how all of those complementarily can give us some constraints on the effective field theory of gravity in a regime that you may be interested in for gravitational waves. Okay, so let me start with the constraint on the scale, and just to give you a little bit of perspective of what you may or may not have in mind. If I just consider, for instance, GR plus all the standard model particles, which are really irrelevant for what I'm going to talk about today, but people are sometimes considering dark matter particles as light as 10 to the minus 22 electron volts. So this is what is typically considered for axionic dark matter without being necessarily so much of a big issue. So this is just symbolic. Let me imagine I have some light dark matter particle. If I consider integrating out these massive particles, which are very light, but still massive. So if I'm considering an EFT below that scale, that very light scale, then I would expect to lead to corrections of the EFT, which are captured by the scale of this massive particle. So if I put the mass of dark matter being as small as, let's say, 10 to the minus 20 electron volt, that would correspond to the cutoff of this EFT. Sorry, the cutoff is 10 to the minus 20 electron volt here. This will correspond to this parameter here, M, which is roughly 10 to the 3 electron volt. So this is a relatively low scale, and it's not even as low at all to what you would need to have in order for those operators to be, in principle, detectable with future gravitational waves observations. So already this is pushing you in a very, very low regime, and so you typically would expect more to need to integrate out tree level of higher spins to being able to see any effect at that level. So you may wonder whether this is in principle problematic and whether you should have observed that from another perspective. From the point of view of the low energy effective field theory, you have corrections to, let me imagine, this is not even necessarily an on-shell mechanism. Let me imagine how those operators would lead to three graviton exchange, for instance. It doesn't need to be that, but just as an example. So in GR, you would have the leading contribution scaling like the energy over the Planck scale. And then if you work imperturbatively in the low energy effective field theory below the mass of the dark matter particle, you have corrections which scale like the energy scale that you're working with. This should really be a Lorentz invariant quantity, I'm just symbolic here, over this scale m that you consider. And it's a perturbative expansion in this sense. So this works out if you're sufficiently low energy scale, but it doesn't mean that if you're working out at high energy scales, you're going to be completely overwhelmed by those effects. Typically, there's a resummation process that comes in. And for dark matter, definitely this is not something we're worried about. We're not worried about detecting very light, massive particle at the LHC through pure gravitational exchange, because if you work to sufficiently high energy scales above the mass of the particle, then all of these will sum into leading something which is very small. So the EFT you're working out here is no longer valid at a much larger energy scale, and the effect of all of those things that you think would otherwise be large will sum to give you something which is quite small at high energy scale. And so typically the same type of things could happen for this type of effective field theory. So you should really think of it as a low energy effective field theory at very low energy scales, and at higher energy scales, if you're interested in solar system physics, for instance, all of this would lead to potentially small corrections. Irrespectively of that, you should accept the fact that this will require energy scales which is much beyond the standard model physics, well beyond the Planck scale. So there's already some naturalness considerations to keep in mind there. Potentially, this will be in a decoupled dark sector, and I say not necessarily dark matter, dark energy. This doesn't necessarily need to have the insight on cosmology that you would want it for dark energy and dark matter, but it should be in a completely decoupled dark sector, coupling only with gravity. Otherwise, we're doomed from the get-go. For the dimension 6 operator, the coefficient here, we typically capture the scale of SUSY breaking in this dark sector. So if you are imagining a completely supersymmetric dark sector by itself without coupling to gravity would be supersymmetric, then you would expect this coefficient here to vanish. With these considerations in mind, and this is really up to you to think you're swallowing too much or not, then in principle, there is a small window of opportunity to probe this type of operators with future gravitational waves. It's a very small one, but at the moment it is still technically open, I would say, until it gets closed down soon. So this is the consideration about the scale. Now let me put some considerations about those coefficients themselves. I already started talking about this coefficient C3, mentioning that it may be linked to supersymmetry breaking in the dark sector. And I'll try to give you some consideration of what to expect for these different type of coefficients. I should say when I parameterize it like that, I really think of all of these operators to be of order 1 or to be 0. It makes no sense for me in this parameterization to have them being very large. Now we had a talk 2 weeks ago, and I'm not going to go through it very much in details, but there has been some very important considerations in connecting this low energy effective field theory with some potential standard high energy completion, which would be unitary, local, Lorentz invariant, and causal in the sense of the amplitude being analytic in the appropriate region of the complex energy square plane. And that leads to some bounds on derivatives of the amplitude with respect to the energy square, which has to be positive. And this is really a reminiscent of the optical theorem. And actually, there's an infinite number of these considerations that you can apply directly within the regime of validity of a low energy effective field theory. So even though these are considerations that come from what you expect the high energy completion to satisfy, those considerations have to be true at low energy already for them to have any chance of enjoying such type of high energy completion. And so if I consider this infinite number of bounds that you can consider in practice, they're really perturbative as well. So there's a leading bound in the non-gravitational setup that would come in from n is 1 here, which would be the bounds coming from elements here being positive, if I expand the amplitude in powers of n squared. And then there's an extra leading order bound, etc. So this is in the context of a non-gravitational effective field theory. But in a gravitational context, you can see here, there's a pole, what we call a T-channel pole. It really corresponds to the gravitational exchange pole, coming from the fact that you have a spin 2 particles coming in the game, and the residue of this particle has grows like the spin of these particles. So in the context of gravity, it goes like s squared. And so it compromises the direct applicability of the positivity bounds at the leading order. Thankfully, there's been some very nice development by infinite impact parameters done by some people in the community that allows you to push beyond those type of bounds. But in practice, for what purely gravitational bounds are concerned, what it means is that it really corresponds to putting bounds on C4 or C3 squared. That's a typical type of gravitational bounds that you can expect. So what I'll do in the next 5 minutes, yeah, thank you, is to, instead of applying these positivity bounds directly at the level of the scattering amplitude, I'll try to go directly about this coefficient by considering a slightly different configuration, which is actually relevant for what we're interested in. And as a condition of causality around black holes in this type of effective field theory, which is sensitive to slightly different combinations of the coefficients. So what I have in mind is very much the same thing as looking at a prism and understanding, and I hope it didn't translate into prison. A prism, it's really trying to understand how the notion of causality or how the different speeds gets changed when you're considering the evolution of waves in a medium. Of course, what I mean by a medium is slightly different. Instead of this prism, I'm going to consider a black hole. And the type of interactions that you typically think of light with the medium itself is really captured by the operators themselves in the EFT. That's what captures how the gravitational waves will be interacting with the field that you have integrated out. And what I'll ask is the requirement, micro requirement of causality is a requirement that there's no resolvable time at bounds with respect to the null geodesic as set by the local metric. So that will be my requirement. I should say, as soon as I say that, it really tells you that there should be some departure from liminality, and we should be worried about any departure from liminality because we know we have a very strong constraints on the speed of gravitational waves from the neutron star merger with optical counterpart. I have to say here, the level of departure from liminality is well below the realm of detectability. So it's not like I'm going to use this experiment to put constraints on this type of EFT itself from the variation of the speed. Rather, it's a purely theoretical consideration, understanding if you possibly have any potential violation of causality in this type of experiment will allow you to determine whether you should consider this type of model or not in the first place. And if you can, if you think it is viable from a theoretical perspective, then you can go and use a different type of observability or detectability from the waveform, for instance, to observe those type of operators. So let me just skip through that because I don't have much time. So I'll be considering some gravitational waves, some fluctuation on top of my modified black hole metric. So this is not quite Schwarzschild. It has corrections coming from an effective field theory. And I'll do what everybody does. I'll look for my master mode corresponding to the evolution of gravitational waves in that geometry. And so the gravitational waves will see a slightly modified potential. And from that modified potential, which depends on the frequency itself, I can already symbolically, that's not what we want to do, but just to give you some insight, I can already symbolically read out an effective speed for my gravitational waves. And you see that it departs from one. It departs from one. It is allowed to depart from one because you are in a medium that spontaneously breaks Lorentz invariance. So the model itself is fully Lorentz invariant, but locally, because of the black hole, it spontaneously has broken it, just like the prism, if you want. And so it leads to a small departure of the speed of gravitational waves as compared to the null geodesic. And I should point out, it goes back to 0 at the redress horizon, and this is as it should be. There's no violation of any of EFT in any way in this sense. Okay, so what we can do now is scatter gravitational waves through this potential and see how they get affected. So as I scatter gravitational waves through this potential, which includes corrections beyond, coming from the operators beyond general relativity, I'm going to have a small phase shift that I can measure back at infinity. And from there, I can work out a time delay. Now, if this time delay here, so you have a contribution, which is the standard GR correction, the standard GR contribution, the Shapiro effect, and then you have additional corrections that are coming from the EFT you're considering, from the operators you're considering, from the fact that gravitational waves are indirectly coupled through these operators to the field that you have integrated out along the way. And so we expect this to be always negative, we expect this to be always positive because it corresponds to the interactions with the fields that you have integrated out along the way. But if this ever becomes negative, then it corresponds to a time advance, and that is typically, related to a violation of causality. It's not completely automatic. It's okay if this time advance is in magnitude small enough, because then it wouldn't be physical. But if it is resolvable in this sense, then it will be indicating a violation of causality. Now, you need to ensure that you still remain within the regime of validity of the effective field theory. So I can talk more about that, but I don't have time. Let me just give you the upshot. In order to ensuring that you remain within the regime of validity of your effective field theory, you need to consider frequencies, or you need to consider some elements for which you're below that line. This is for the various multiples. And in order to have a resolvable time advance, you need to be above that line. So if you want, this is the line where the frequency is such that you would have a resolvable time advance. So what you consider being a violation of causality. And this is the line for which you are remaining within the regime of validity of EFT. So any region in here, if you're allowed to put yourself in this region there, you could potentially have a violation of locality as set up by the local metric. And so avoiding the very presence of such considerations, you really need to push the cutoff of EFT to be large enough so that you are always below this region. So in this sense, that gives you, for any black hole consideration you want to have, if the coefficient of the dimension 6 operators was negative, that would tell you that the mass parameter that you need to consider has to be larger than roughly some quantity related to the Schwarzschild radius of the black hole that you're considering. Now, it doesn't matter too much what you're considering here. We know already that there's black holes which are as light as maybe 5 solar masses, maybe a little bit less. Maybe they could be as small as the fundamental scale of quantum gravity. It doesn't even matter at this level, because this is already, the Schwarzschild radius is already such a small scale that already puts the mass well beyond what you can expect to probe with gravitational waves. So for all intents and purposes, we should never be able to obtain any coefficient C3 which is negative, unless you would be violating causality or violating some other type of effective field theory considerations that you're considering. Okay, so let me not go through that and leave my conclusion slide here. Thank you.
Thank you for a very nice talk. So let's hear questions from Zoom and from the audience. Julio?
Hi, thanks for a very nice talk. So about this experiment where you're scattering something off the black hole. So what is the extra mileage that you get intuitively compared to the kind of old argument by Camaño, Malazena, Chicodeov, etc., which was also this kind of scattering, it was in a perturbative amplitude, but one also has to resum a series of diagrams. I guess here you're resumming a different series of diagrams that build up the metric.
Yeah, I think we're asking a slightly different question here. We're just asking for the time delay, right? Which I think they're more. We're just asking for this quantity here. I think they
were also looking at the time delay, right? They were also asking that the time delay is negative.
So which paper?
Camaño, Malazena.
Oh, I see. Okay, so this is for Gauss-Bonnet operators in higher dimensions. Yeah, so in this case, this is automatically satisfied. What they want is simply this whole contribution here to be positive. And for us, this is always satisfied. This is not an issue. I mean, you really needed to violate the regime of validity of the EFT much more to being able to see such a problem there. We're not saying this is not. You're never able to enter this regime if I ensure that I'm always within the regime of validity of my EFT. So what I'm asking is a slightly refined requirement, and I haven't gone through that, but actually in some contexts, at least, well, without gravity and in some other contexts, this is actually closely related to some of the direct positivity bands that we're observing. So I'm asking, related to the local metric, for the difference coming from the EFT corrections to be not to lead to a large time advance. And the reason for that is I'm considering the local metric as being the universal metric seen by photons, for instance, seen by any massless fields, potentially seen by high frequency gravitational waves that had a way to resum, even if that's speculative, at least it's the metric seen by massless field. And so in comparison to the null geodesic set up by that local metric, I'm asking for that not to be any support outside that light cone. Yeah. So if I were to apply those criteria in here, I have a graph where I didn't have a. You can put the same type of requirement here, and it's instead of having that, you have some conditions which are always roughly trivially satisfied if you are in the regime of validity of the EFT. But that's the case for them as well. If you are in the regime of validity of the EFT, you wouldn't see any time advance. So it's all consistent, yeah. I have to say this is in higher dimensions technically, and then for Gauss-Bonnet operators, you can do this in higher dimensions. There's a small dimension dependence, and so the effects are typically weaker in higher dimensions because it gets diluted. So 4 dimensions is actually where you have the most chance of seeing those effects. But that's just a small technical. That's possible, yeah.
Yeah, so thanks for the nice talk, Claudia. So I had a question about, so you talked about these Riemann to the third terms and then Riemann to the fourth. So just by sort of power counting, should we expect that we'd always see the Riemann to the third term first and like a gravitational wave observation or something, or is there some theoretical reason we might expect the coefficient in front of that to be suppressed compared to the next term?
So you can have the coefficient of the Riemann, the dimension 6 operator to be suppressed, for instance, by supersymmetry argument. So if in that sector it's completely supersymmetric, it could be 0. In principle, it can be suppressed by other effects, semi-cancellations. So you don't expect it to be overly dominant. It would be unnatural to have it being large as compared to all the others as a dimensionless parameter. But in principle, by symmetry argument, you could imagine a situation where it is suppressed, or it is 0.
Yeah, thanks. Oh.
Yeah, so in these effective theories of gravity, you know, are there interesting corrections to the black hole solutions themselves that we could go hunting for? You know, so for example, some small love number or something.
Yeah, so I need to ask you. I don't know exactly in terms of the love number. The solution is modified ever so slightly. I didn't go through that. So typically you would have some corrections of this form where those functions here are not even, if you want to keep this frame, are not even the same. They are ever so slightly modified. The position of the black hole, the horizon itself, is ever so slightly modified as well. It can go inside, it can be outside the previous one, but that's okay. And what you see is that once that happens, everybody sees the same horizon, and it's really a consistency check. So yeah, it does get perturbatively changed. These corrections are quite small, really very small. So in the inspiral phase, this is going to be very suppressed. Yeah.
And yeah, I would like to ask you of this effect instead in the ring down. So how much the quasi-normal mode frequencies would deviate in this scenario? You mentioned that the modification is small, and I would like to ask you more specific details on this.
Yeah, so it's suppressed by that parameter here. So you can only make sense of it if you're in an EFT where if in a hierarchy where this is well below your cutoff or the scale. So this is always by definition gonna be small. Now it depends a little bit how small you want the scale M to be again, but typically you probably don't want it to be much larger, much smaller than that. So you can see that this is going to be very small effect.
And will this correction affect, this small correction affect the prompt ring down, or would you expect to have like very tiny gravitational wave echoes after that?
No, this is for the ring down itself. Yeah, and then for the inspiraling, you have additional velocity suppression. Yeah.
Okay, thank you.
Yeah.
Thanks for the talk. I want to ask some question about the S matrix positivity bound.
Mm-hmm.
So if I understand correctly, is this EFT built on the flat space background?
Yes. Yeah, that's in flat space, but the corrections to flat space are very small. Are you worried about the curvature of the black hole, or are you worried about something else?
Zeta.
The zeta is so small. the scale of the zeta it's at the same level that I didn't put the cosmological constant in. If you want to apply those for cosmology, if you want to apply that for the EFT of inflation, even for the EFT of dark energy, then you need to take that into consideration, particularly if you are built in this breaking of Lorentz invariance into the formulation of EFT, then it is relevant. But if you're interested in black holes, that's not going to be so relevant here. Yeah. The fact that you're in the zeta is not relevant for those. The suppression is really extremely small. And you're considering effect from the Hubble curvature, which is 10 to the minus 33 electron volts. Yeah, so the effect of the zeta to those bounds at those level is, you're interested in local physics, right? As opposed to the size of the universe physics. And so the scale of that is very small. You can still set up your experiment. You have a black hole there, you do some scattering where you're still asymptotically kind of locally flat before you see any insight from being on a cosmological background. Yeah. It's very different if you're interested in applying those bounds for inflation, for instance, and that's very different because you can't, get away from that. Yeah.
So I wanted to ask about the scenario you mentioned where you're in the regime of validity of the EFT early in the inspiral only, and then there's presumably some transition. So in a scenario like that, I guess we already know that after this transition, it looks something like general relativity.
Yes.
Is there any understanding of what a theory might look like in that case, what corrections to expect?
No, I mean, if you have a very big hierarchy, if you're like many orders of magnitude above that, is not completely unnatural to expect that things would resum and could look a little bit like GR again. But straight after, I would say you have to resum order 1 effects. No, I don't know. So I think what they've done here in that nice paper, you just throw away the signal. Right. Yeah. Sure. Yeah. So I guess this is my question. This is my question. I don't know. And we probably never know, because you need a quantum realization of what's going on above that scale to really saying how this is going to resum to something else. Particularly if you thought this was coming from higher spin, then is it the scale of quantum gravity that comes in there? I don't know how to resum that. You may think, well, this is not actually coming from higher spin, it's coming from lower spin, and so many of them that gives a big effect, but still, this is highly unclear. Yeah.
Thanks.
Yeah. So I don't know at all.
Let me just check if there's any questions on Zoom. Anybody who has questions on Zoom are welcome to speak.
Yeah, but I would say that this is, you have to be very careful, because there's going to be a transition, and expecting things just to look smoothly. I mean, yes, they will look smoothly, but they don't need to look anything like GR in the meantime.
Right, and we don't see any particularly obvious so far violations of that nature. So
yeah, absolutely, yeah. To be honest, this is beyond my realm. I'm there from the theory point of view.
Sure.
How one would go and put that in practice is not. I would imagine really you need to split your waveform into two. I mean, there will be some events like in LISA where you just see the early in spiral, and that would be ideally suited for that. Right. And then you may expect things to be at a much larger scale beyond it when you go to LIGO. Yeah.
Yeah, we have a question over there.
Hi, thank you for the nice talk. I wanted to ask about the Riemann cubed coefficient statement that you made. So if I remember correctly, if I integrate out a minimally coupled fermion at one loop, I get a negative contribution. So what is the statement of causality in that case? Yeah.
So this is assuming I'm putting accounting, which is, I don't know if you can see it, which is with a Planck scale enhancement. If you're dealing with loops of fermions or any spin half particle, you are gonna have, with loops, you're gonna have Planck scale suppressed effect. So then the effect you would see is Planck scale suppressed, and you won't see any time advance. So this statement is really if you're considering some tree level completion.
But I would get a contribution if I had like a large number of fermions, right?
Yeah, so but your cutoff is then much smaller as well.
Ah, okay.
So the regime of validity is much smaller as well. So in that case, you're not going to observe anything, and you're not going to be in violation with causality. So you have to put that in context in a situation where you expect your regime of validity to be large enough so that you can potentially detect something. So this is the prior. However you want to achieve that, I don't know. Once you have that in mind, then it's a meaningful question to ask, when is this time advance resolvable in the regime of validity of this EFT? But if you're considering loops of anything really, it'll be positive for bosons and negative for fermions, it will always be the case that the Planck scale suppressed, and you're never going to have them being resolvable. Yeah, no, it's a very good question. Yeah, so I guess,
we're almost out of time, but I think there was one more question. No? All right. No more question then. So let's thank Claudia again.